Hey guys, in this section we're going to be covering exponential functions. All right, so an exponential function is a function in which x, the input, is part of the exponent. For example, we have this, f of x equals a to the x power. Okay, so a, where that position is, we consider that to be the base of our function. And now our variable, which is x, is now in the exponent. Okay, so let me show you how this is different than the functions that we've looked at before. So typically, we've usually had a function like f of x equals x squared, where x was our variable, but it was in the position of the base, and 2 was our constant, but it was in the position of the exponent. So for example, if I were to do something like f of 3, I would plug in 3 where x is, which would result in 3 squared, and we know that 3 squared is 9, okay? Now, what we're looking at now are exponential functions. So instead of having something like f of x equals x squared, we would have something f of x equals 2 to the x power. So now the 2 is in the position of the base, but x is in the position of the exponent. So if I were to do that same calculation, f of 3, 3 would not go where the base is. It would go where the exponent is because that's where our variable is. So we would have 2 to the third power, which would give us an answer of 8. Okay? So the functions we're going to be looking at in this section are when our variable is in our exponent. Okay? And that is an exponential function. So be careful about distinguishing between the two. Okay? All right. Since we're going to be looking at exponential functions, it's important that you guys remember your laws of exponents. So if you don't, here's a quick refresher. So our laws of exponents say if s, t, a, and b are real numbers, with a being greater than 0 and b being greater than 0, then we have the following. So our first rule here says if we have like bases, when we multiply them together, we add their powers. Okay? Our second rule says, all right, if we have a power raised to a power, we multiply the powers together. Our third rule says if we have a product, remember a product means you have two things being multiplied together, and you're raising that product to a power, it's the same thing as raising each factor to that power, okay? This rule here says that 1 raised to any power is just 1. Anytime we have a base raised to a negative exponent, okay, we can make the exponent positive by taking the whole expression and moving it to the denominator, okay? And if you have a fraction, it's the same thing as raising each one of those numerator and denominator by the power. And here, if you have any base raised to the 0 power, it's equal to 1, okay? So those are going to be useful to us, especially when we start to solve exponential equations. All right. So here's our formal definition of an exponential function. So it says, an exponential function is a function of the form f of x equals c a to the x power, where a is a positive real number, with a being greater than 0, a cannot equal 1, and c cannot equal 0 is a real number. The domain of f is a set of all real numbers, and the base a is the growth factor. And because f of 0 equals c a to the 0, which equals c, c is called the initial value. Okay, so that's our formal definition of an exponential function. Okay, so let's get into what the graphs of exponential functions look like. Okay, now depending what your base is, you could result in two different types of graphs. Okay, so for this one, we are going to look at the exponential function graph when we have a to the x, but a is greater than 1. Okay, if your base is greater than 1, then your domain is going to be all real numbers, negative infinity to positive infinity. Your range is going to be all positive numbers, which is 0 to positive infinity. You aren't going to have any x-intercepts, okay? Notice that this graph does not cross the x-axis, okay? So it has no x-intercepts. It has one y-intercept at 0, 1, okay? And it has a horizontal asymptote. So remember we talked about asymptotes when we talked about rational functions? You can see here on the graph there's this dashed line. That is its horizontal asymptote, okay? The graph is also going to pass through the point 1a. okay? We can also see that this function is going to be increasing over its entire domain. Remember, if we think about graphs like roller coasters, we would be rising from left to right. So this graph is increasing, okay? This function is one-to-one, okay? Remember, one-to-one means that it passes the horizontal line test. So if I were to draw horizontal lines to my graph, each line is only going to pass through my graph in one place. So it's one-to-one. All right, and the graph is also smooth and continuous, and it has no corners or cusp or gaps, okay? So there is our first graph. Now, depending on what book or resource you're looking at, sometimes they will call this same picture a growth model, okay? So same properties, just a different name. So sometimes they will call this a growth model if your base is greater than 1, okay? All right, now let's look at the second scenario. We will have this exponential function graph if our base is between 0 and 1, okay? So this one has similar properties. You'll notice that this graph is decreasing as we move from left to right, okay? You'll notice that it has the same domain. It has the same range as the previous one. It still has no x-intercepts. It still has the same y-intercept, okay? It still has this horizontal asymptote, okay? The graph passes through that same point, 1a, but instead of increasing, the graph decreases. It's still one-to-one, and it's still smooth and continuous with no corners or gaps, okay? So the only thing that's majorly different is that this graph will decrease on its domain, whereas the other one increased on its domain, okay? So once again, if you're looking at another book or resource, they will call this graph a decay model, okay? Because it's decreasing as you move from left to right. So your two types of exponential functions are growth and decay. Those are their two categories, and we distinguish one from the other based on the base, okay? Awesome.